Just a minute. Okay. Okay. Good. So good morning, everybody. Before I start, I would like to thank the organizers for this very nice conference in this very beautiful place. I was missing a bit the beaches in Brazil, so thank you, Tommaso. And also, I would like to thank to the opportunity to present to you the new results we have been doing in 2D Bose gases at Collège de France. And in order to talk about the pattern formation in such systems, I would like to start with a brief introduction on how miscible and immiscible fluids appear in nature. So it's well known that a system with two classical fluids can be miscible or immiscible depending on the comparison between the interactions of each fluid with itself and their mutual interaction. This will also happen when dealing with quantum fluids. And in such systems, the system is described by a pair of coupled Gross-Pitaevsky equations in which the interspecies interaction represents the coupling term in the system. In this context, one can define a miscibility parameter that says that the system is miscible if delta is larger than 1, and immiscible if is smaller than 1, and immiscible if delta is larger than 1. So over the past 20 years with experiments in cold atoms, many groups have been focused on studying the properties of these systems in the ground state. And with the use of Feshbach resonances, it was possible, for example, to cross between the two different miscibility regimes. So here I'm showing you 3 examples of such a crossing, but there are many other groups working with Bose-Bose mixtures, not to mention also the works done with fermions. On the other hand, less attention has been done to study the dynamics of these systems after quenches between the two different miscibility regimes. And these quenches can be performed, once again, with the use of Feshbach resonances, or by producing a superposition of 2 hyperfine states of the same atomic species. In the case of quenches to the immiscible regime, the excitations of the wave functions will develop a modulation instability in which long wavelength density fluctuations will grow exponentially, with growing rate given by this quantity here, where C minus square is a negative constant that depends on the miscibility parameter and on the speed of sound of each fluid. Therefore, this growing rate will depend on the density of your sample, and there is a mode that grows faster, which will eventually dominate the dynamics, creating equally spaced domains of each fluids. So such modulation instability in quantum gases have been observed first in 3D gases, in which the appearance of domains was observed for different times of the evolution of the system. However, the limitations in the detection of 3D samples makes it difficult to qualitatively study the dynamics of this growth of these patterns. And in this direction, experiments dealing with one-dimensional gases were able to visualize the formation of equally spaced domains in each component, and also to study the long-time evolution of these systems with the merging of these domains. One thing that these 2 experiments share is that both experiments were done in harmonic traps, which make us wonder which is the mechanism that triggers the modulation instability. Is it only due to the fact that we have an homogeneous density profile at the beginning or not? So in this talk, I will show you some preliminary results on observing such a modulation stability in uniform 2D Bose gases. So our experimental setup is simple setup. So we work with with rubidium-87 atoms, and in order to produce 2D atomic gases, we developed a 2D box potential that combines an accordion lattice and a digital micromirror device. So the accordion lattice that is drawn here in this drawing, it's responsible for the confinement along the vertical direction. And since we can change this confinement, we can load large atom numbers into the 2D regime. In plane, the DMD device enables us to create any arbitrary in-plane potential we want, as it is illustrated in the set of absorption images done in our experiment. So in order to produce now the two-component Bose gases we want to study next, our experimental sequence starts with 2D Bose gas, the generate 2D Bose gas, with the atoms in the 1,0 state, trapped in a box potential with side equals to 40 micrometers. And we perform a microwave pi/2 pulse in order to transfer half of the atoms to the 2,0 state and create a slightly immiscible mixture with delta equals 1.03. Then, once we have the mixture produced, we can follow its evolution for different demixing times and perform a stative selective imaging procedure in order to observe the density profile on both components here. So our question is, how does the system evolve? And on considering the denser cloud we can produce, the system evolves like this sequence of images here, in which the demixing time is in milliseconds. So we clearly see for long times the appearance of well-defined domains on both components. And the shape of these domains was confirmed by the results from numerical simulations in the group. So at the very beginning, the simulations match qualitatively well with our data, but at long times we still see some deviations, and this could be due to the fact that we do not take into account the losses that we have in the experiment, and also because the simulations are done at t equals 0, so we are improving then at the moment. But anyway, we can focus on our experimental data, and here we can see that we have two timing intervals in which the system behaves differently. So first, at short times, the initial dynamic is dominated by the independent growth of modes with different k vectors, as I introduced you at the beginning of this talk, as a result of the modulation instability. For long times, however, we see the appearance of well-defined density modes and their decay into smaller k vector modes as a function of time. In order to better characterize dynamics, we develop an analysis procedure that takes into account the shape of the domains we observe. So first, the boundary conditions of our box potential has a great influence on the domains, on the shape of the domains we see. If it was a disk, we would see a different shape here. So we take this into account, and also the symmetries that are kept for all times here that are identified with these lines and these arrows. So with this in mind, we define a set of modes in order to calculate the overlap of our density profile with these modes and study the overlap coefficient as a function of the demixing time. So if we do so for this set of data that I just showed you, we see this set of curves in which I'm showing you the overlap coefficient for different modes with different colors as it's identified here. And this 1 and 2 represent the two different time regions that I just explained before. So we are going first to focus on the initial dynamics of the system, and by zooming here on this initial region of the graph, we see that modes with different mode number grow at different rates, and we can perform an exponential fit in order to extract omega minus k that I just introduced you before. If I do so, what I see is a curve like this, which peaks around the mode number 5 here. And if now I change the density of my cloud, what I observe is this set of curves. So not only the value of the growing rate decrease, but if I look at its peak here, we see that the peaks occurs for a smaller mode number as I decrease the density of my sample. So these peaks represented the fastest growing modes of my system, and I can write the expressions for the characteristic wavelength of the fastest mode, and also the characteristic time, in order to plot these quantities as a function of the density of my sample. And what I get are these two curves for the time and for the wavelength, and all my points are slightly below the theoretical curve for an infinite system, that are these two that I show you on the previous slide. So even if my data do not match with the theoretical curve for this infinite system, they show a similar qualitative behavior, and which can be confirmed by changing the size of the box that I trap the atoms. So if I do this, I change the size of my box, I see that all points follow the same tendencies, confirming this behavior. So we are now working on the simulations in order to build the same type of curves and do a more direct comparison with our data. So now, if I look on the long-time dynamics of the system, the first thing we see is that each overlap coefficients show a maximum value, and this maximum value happens at different times for different mode numbers. So these times could help us understand how is the mechanism through which the system reaches equilibrium. So if I plot these times, so the time for the maximum overlap of each mode number, I get a curve that resembles an exponential. And if I change the density of my sample, I get these other curves here that tend to follow the same, all tend to overlap, at least from at this initial analysis that we are doing. And this was a bit surprising because it means that the decay procedure of the cloud do not depend on the initial density of our sample, differently from the initial dynamics of the system. So we are improving this analysis by performing a Fourier decomposition of our samples that would better take into account the merging procedure that happens at long times in order to have a more conclusive idea of what is happening here. We also did some recent experiments changing the temperature of the system, and we still don't have any conclusive results on what is happening. We see that the patterns are a bit blurred, but they still form even above the critical temperature for the BKT. So we are still exploring this point now. Okay, so in order to finish, I would like just to give you an idea what's coming next on our experiment, dealing still with two-component Bose gases. And now our idea now is to be able to do a localized transfer of the atoms to a different hyperfine state. And this we do with a two-photon Raman transition in a setup that combines an accordion lattice and a DMD in such a way that we can do a localized transfer and also transfer linear momentum or not, depending on the experiment we want to perform. So we have several projects in mind for this new, with this new tool. So first, when considering no momentum transfer, we want to explore the interface dynamics of two superfluids. So here, this black contour here is my box potential. So I transfer half of the box to another hyperfine state, and we can study how this interface evolves with time. So we expect to see two other types of instabilities happening depending on the initial conditions of our experiment. So Kelvin-Helmholtz instability or Rayleigh-Taylor instabilities. And we are going to look for this soon. Also, what we are trying to do right now in the lab is experiments dealing with the diffusion of impurity in a superfluid bath. So our idea is to investigate the existence of an anomalous diffusion in such a system as it is proposed on this reference here. And when dealing with momentum transfer, we want to see the effect of a moving impurity in the superfluid properties of the bath, and also how the bath affects this impurity. Does it deforms, and what happens? So far, what we saw was the suppression of diffusion. So this time, for example, is longer than this time with the same parameters, and we see that it doesn't diffuse, and we still are trying to understand why. So yeah, I think there are a lot of nice things to do in the very near future in the experiment. So with this, this is the team that had working in the rubidium 2D experiment. So we are a lot of people. Jean-Loup just left. He was the senior PhD student when I arrived. And Brice just started his PhD with us now. And with this, I would like to thank you all for your attention.
Thank you very much. Questions?